Welcome all. In today's particular discussion, we are going to discuss about Klein's 4 group. So, Klein's 4 group is a group of order 4, which is abelian but not cyclic. So, such groups are called Klein's 4 group. It is not just a single group but a family of groups of order 4 which satisfies these two conditions. First of all, it has to be an abelian group, and second is it has to be a non-cyclic group. Such groups are called Klein's 4 group. So let us understand these through an example. Let us consider a group U of 8. So U of 8 consists of elements 1, 3, 5, 7. Under multiplication modulo 8, it's gonna form a group. Let us see. So 1 into 1 is 1, 1 into 3 is 3, 1 into 5 is 5, 1 into 7 is 7. Under multiplication modulo 8. So 3 into 1 is 3, 3 into 3 is 9. But under multiplication modulo 8, 3 into 3 is gonna be 1. And 3 into 5 is 7, 3 into 7 is 5. So 5 into 1 is 5, 5 into 3 is 7, 5 into 5 is 1, 5 into 7 is 3, 7 into 1 is 7, 7 into 3 is 5, 7 into 5 is 3, and 7 into 7 is 1. So clearly you can see all these elements are from a set U of 8. So we can say closure law holds, and you can also verify associative property is also gonna hold, and a third property which is identity element. So let us search for a similar row or a similar column for these. So first row is similar row, so identity element is gonna be this element, this corresponding element, which is 1. Or else if you consider a similar column, so you can see this element is going to be identity element, which is 1. So let us check whether all the elements in U of 8 has an inverse or not. So we can see each row has identity element. So every element in this group has an inverse. So we can say inverse exists. So clearly U of 8 forms a group, and also you can see it is not just a group but an abelian group. So you can see this is a symmetric, so this is an abelian group. So to be a Klein's 4 group, it has to be non-cyclic. Okay, let us consider an element 1. So element 1 is an identity element, so it's going to generate only identity element itself. So let us start with 3. So you can see neither 3 nor 5 or nor 7 is going to generate the whole group. So this group has no generating element. So U of 8 comes under Klein's 4 group, which is abelian but non-cyclic. Other examples for Klein's 4 group are U12. You can construct Cayley's table and see it is abelian, and also you can see it is non-cyclic. So here are the other examples also. Z2, direct product Z2. So Z2 has an element 0 and 1 and 0 and 1. You can take the combinations 0, 0, 0, 1, 1, 0 and 1, 1. So 0, 0 is going to act as an identity element, and remaining element are self-inverses. So since they are self-inverses, all of all these elements is gonna be, order of all these elements is gonna be 2. So there is no element of order equal to the order of group, which is 4. No element of order 4. So from one of the properties of cyclic group, we can say it is non-cyclic. Since there is no element of order 4, it is non-cyclic. So here also there is another example which is general. You can go through this. So these are the examples for Klein's 4 group. Thank you.